Oh, you want some handouts, don't you? Right, here we go then. So, today's session, what we're going to look at, significance or hypothesis testing. So, we're going to have a look at what it is, look at the null and alternative hypotheses. We're going to look at hypotheses for comparisons, levels of significance and confidence, critical values and regions, detailed tests. We're going to look at the methods of significant testing for population means and look at problems involved. So that's the session. Get all that done. Hypothesis testing. Right. Industrial applications often involve making decisions. For instance, which of two processes is better for producing product? Whether to discontinue production on a machine because there's too many defects, or because there's too many defects. Whether monthly or bi-monthly servicing of a machine is the most cost effective. These decisions are based on finding the mean and standard deviation of some sample data. In reaching these decisions, certain assumptions are made which may or may not be true. So that's what your hypotheses are, as you'll see in a minute. You're making an assumption, or you're saying something is true, or you want to test whether that's true, and then the statistics will help you to decide whether it's true or not. Okay? So they are your statistical hypotheses, just hypotheses, concerned with statements about probability distributions in terms of where you would expect there to be a normal distribution like we were doing last week. Alright? So, hypothesis example, the null hypothesis. In order to confirm that the throw, this is a simplified example. In order to confirm that the throwing of a standard dice is fair, i.e. unbiased, you could make the hypothesis that the number 5 should occur with a probability of 6 dice, so 5 should come up 1 in 6 times. Such hypothesis is called the null hypothesis. That's what you would expect to happen. Yeah. And is an initial statement. We use the symbol H subscript O to indicate the null hypothesis. If P is the probability of throwing a 5, then you would write like so, HO colon P is equal to 1/6. That's your null hypothesis in mathematical terms. And there it is, it works. So the null hypothesis is that the probability of throwing a 5 is 1/6. Alternative hypothesis. So you might be saying, I think this dice isn't fair, and that's loaded one way or the other. So any hypothesis that differs from the null, in this case 1 in 6 times, is called an alternative hypothesis, and it's indicated by the symbol H subscript 1. Thus, if after many throws it is found that a particular dice is biased and that a 5 only occurs on average once in 7 throws, then several alternative hypotheses may be formulated, such as H1 P is equal to a 7th, so there you'd be saying the probability of getting a 5 is 1 in 7. You could say that the P is less than a 6, so you're making that up, that it is less than a particular number, less than the null hypothesis. You could say that you think H1 is between an 8th and a 6th, and you could say that H1 is not equal to a 6th. And that would cover both sides of the story. Okay? And more about that in a little while. all of which are valid alternative hypotheses to the null of P is equal to 1/6 for a fair dice. All right, and then the statistics that did after that would prove whether the results you got were random and actually the dice is fair, or would prove the alternative hypotheses that this dice is loaded away from the number 5. All right. Hypotheses for comparisons. You can also use hypotheses where we wish to make comparisons. For example, if we wish to compare the strength of two different metals, you might formulate the null hypothesis that there is no difference between the strength of the two materials. So you'd say if the forces that the two metals can withstand are F1 and F2, you could make the null hypothesis that F1 is equal to F2. The strength of those two materials are equal. If you then wanted to attempt to prove that the strengths of these two materials were not equal, i.e. reject the null hypothesis, then you would need to prove on one of the possible alternative hypotheses. That is that F1 is not equal to F2. In that case, your alternative hypothesis that F1 is either stronger or weaker. So you're looking at both sides. You could make the hypothesis that F1 is less than F2, or the alternative hypothesis that F1 is greater than F2. That's just looking at one side of the data. Okay. Everybody all okay with that so far? And I know it'll become clearer when you have a look at the problem. All right. Levels of significance. It is possible that errors can occur when interpreting the results of hypotheses tests. And these can be of two types. Type 1 errors are where a particular hypothesis has been rejected when it should have been accepted. So you've chosen something wrong somewhere, and actually you haven't got the right answer. And again, type 2 errors are where a particular hypothesis has been rejected. Okay. Now, there's quite a bit of stuff. I don't have to go through how you work out what the levels of type 1 and 2 errors are for this course. If you're interested, and I bet you in, you can find that information in your Bird mathematics books if you wish to. Okay. The likelihood that type 1 errors might occur, so that's where a particular hypothesis is rejected when it should have been accepted, right, depend on the level of significance chosen for the test. The level of significance is indicated by the symbol alpha, and the levels commonly adopted are 0.1, 0.05, 0.01, 0.005 and 0.002. They represent 10%, 5%, 1%, 0.5% and 0.2% respectively. Okay? And more about that in a minute. The problems we're going to work with are, I would say, we're going to be looking at using a level of significance of 0.05 or 0.01. The more important it is that you prove your hypothesis precisely, the lower the level of significance you want, because you're asking the evidence to be really good. If you're trying to make a case for the alternative hypothesis, that is. Okay. In significance tests, the following terminology is often adopted. If the level of significance is 0.01 or less, i.e. the confidence level, is the other side of it, is 99% or more, results are considered highly significant, i.e. the results are considered likely to be correct. If the level of significance is between 0.05 between 0.05 and 0.01, the confidence level is 95% or between 95 and 99. These results are considered to be probably significant, i.e. the results are considered probably correct. If the level of significance is greater than 0.05, is greater than 90%, then the results are considered to be not significant. That is, there are doubts about the validity of the results. How you need to be. If you're talking about bringing a new, you're likely to want to be more confident about that's not got certain side effects, for instance, than you would be about a machine making widgets, whether they were big enough, whether they were in or out of top. It depends on the importance of the answer. The use of this terminology suggests the use of a level of significance of 0.5 for probably significant is, in effect, a rule of thumb. And that's why we're going to be looking at problems generally that we're using a level of significance of 0.5. All right. So what does all this mean? Critical values and critical regions. For a set of results to be probably significant, the confidence level of 95% is required for a particular hypothesis to be probably correct. This is equivalent to the hypothesis being rejected if the level of significance is greater than 0.05. For me, for this to occur, the Z value of the mean of the examples, we've done Z values last week, will lie between minus 1.96 and plus 1.96. You'll see where that comes from shortly. It's at the bottom of the page. So the area under the standardised normal curve between these points is 95%. So we're on our normal curve and we're working at a confidence level of 0.05. So we've got of 2.5% either side of the 95% in the middle. Remember, all of that under there adds up to 100%. Yeah? Okay? Everyone happy with that? And we got our Z values here. So the confidence, we're looking at both sides. The Z values are minus 1.8 and plus 1.8. So if your result came between minus 1.96 and plus 1.96, you'd accept the null hypothesis in the middle. If it comes up that, you would reject the null hypothesis and hex alternative because your data has got significant amount of data up in those extremes. Right, always remembering that in the middle. Okay. So on the same page for you, but for me I had to put it on another page. The Z values greater than 1.96 or less than minus 1.96 are called critical values, and the shaded areas are called critical regions. If a result falls in this region, then the hypothesis, and generally that's the null hypothesis, is rejected. The table below summarises the Z values for different levels of significance. 1 and 2 tail tests explained in the next section. So from this, that is actually a 2-tailed test. We're looking for 0.05 level of significance. Z value for a 2-tailed test is minus 1.96 and plus 1.96. Yeah. You can work those out from the other table that I gave you last week as well. You have to just use that table in reverse to what we were using it last week. But no, that's given for you in that table. So that table is going to be useful to you, both for today's session and for any work that you need to do on hypothesis testing in your assignment. Right? I may well repeat it in the assignment if you need it. But at least you know where it come from and what it looks like. All right? So if we went with 0.01 level of significance, you can see that those values would go much further. It'd be minus 2.58 and plus 2.58. These regions would be much smaller that you needed to prove or to accept the alternative hypothesis. Yeah, because you're looking for a more extreme level of significance. So, we've already mentioned this, but two-tailed tests, when a critical region occurs on both sides of the distribution, as shown in figure 2 below, they are as a result of two-tailed or two-sided tests. So your null hypothesis is interested in data greater and less than that of the null hypothesis. In such tests, consideration is about the percentage. For example, if you are required to show percentage of metal P in an alloy that was 50%, then you would do a two-tailed test because the null hypothesis is incorrect, that is either less or more. So the hypothesis for this example would be that P is X% of the null hypothesis. The alternative is that P is not X%. Okay. So that's a two-tailed test if you're interested in size of hypothesis. Yeah. We have one-tailed tests. When critical regions occur on one side of the distribution, as shown in the figures below, they are a result of a one-tailed or one-sided test. In such tests, consideration is given for the values on either the left or the right side of the percentage. So we could be looking for Z values greater than the values from the table. If we are looking at above the mean, if we're interested in values below the mean, we're looking at Z values and you've got your 5% as that whole region either side. So, for example, if a machine is producing faults and the number of default faults D acceptable in a batch is 2 and more than 2 means the machine is stopped and adjusted. This example will require a one-tailed test to write like that figure 3 up. If you look at the above, Z value is higher than 1.645 for top. The hypothesis for this example would be that the null hypothesis is that D is less than 2. We've taken anything less than 2 is okay. Defects, that is. Anything greater than 2 is, sorry, less than or equal to 2. Anything greater than 2 is the alternative hypothesis. Okay. If a manufacturer was testing lamps, this is the other side, and is only interested in those that have a life length L of 1,000 Rs or more, with anything less than that require an action to be taken, a one-tailed test to the left of the page that figure B. So here we're looking for values below because we want to know if we're falling to less than 1,000 hour lamp life, and then we're going to do something about that. So that's a one-tailed test to the left of the distribution. Again, for 5%, for a 0.05 confidence level, all of our 5% is on the left-hand side. Okay. So, significance testing for what's called population means. When carrying out tests or measurements, it's often possible to form a hypothesis as a result of these tests. So, for example, if you've done some tests and you found the boiling point of water to be in that range, 9.8, I'm not going to read them all out, and so on. So you've got different sets of tests as a result of 6 tests. The mean of those 6 results is 100.1 degrees C. Based on these, confidently can it be predicted that at this particular height above sea level, because the boiling point changes as we change height, okay, and at this particular barometric pressure, if pressure always water boils, 100.1 degrees C. In other words, other results based on sampling significantly different from the true result. Insignificant test for population means a random sample is drawn from the population and the mean of the value of the sample is determined. Test procedure studied here also requires that the standard deviation is known. There are methods other. So when you're given one of these problems to do, you're going to be told what significance level to use, and you're going to be given the mean and the standard deviation of the sample. All right? So, let's have a look at a step-by-step example. Now, every bit of work in here for this is laid out in your notes so that you don't need to copy it down and you can follow it along. All right? So, we got this problem where sugar is packed in bags by an automatic machine. The mean mass of the contents of the bag is 1 kilogram. So that's what that states on the label, is we're giving you an average 1 kilogram of sugar. Yeah. Random samples of 36 bags are selected throughout the day, and the mean mass of a particular sample is found to be 1.003 kilograms. So 3 grams over the mean is of the 36 bag sample. The manufacturer is willing to accept a standard deviation on all bags of 0.01 kilograms and a level of significance of 0.05, above which values the machine must be stopped and adjustments made, determine if, as a result of the sample under test, the machine should be adjusted. So we're trying to make a decision, as it appears that the sample is suggestion that these bags are okay, but it happening of 5%. So, population mean, if the context of the bag has a symbol mu, in this case, so the symbol for the population mean is mu. That's what you'd want the mean to be, 1 kilogram. All right? The sample mean, x bar, is 1.03 kilograms. That's from the question. All right? So all okay with that so far? Yeah? sample size is given the symbol n, and in this case n is equal to 36. Note, for this method to be valid, the size of the sample needs to be suitably large, n greater than 30, and it is. Okay. So a null hypothesis for this problem is that the sample mean and the population mean are equal. So mu being the sample mean, x bar being mu being the population mean, x bar being the sample mean. We're saying the null hypothesis is those two are equal. All right, and if we prove the null hypothesis, as you would be interested in, if we prove the null hypothesis, then we won't stop the machine. All right. As the manufacturer would be interested in deviations on both sides of the mean, a two-tailed test is required. So we need to look on both sides, too heavy, too light. Neither is good. Okay? So, both sides of the mean, so we require a two-tailed test, and the alternative hypothesis is that the sample mean, x bar, is not equal to the population mean, so there's your null hypothesis. And if we're in that region, if we accept the alternative hypothesis here, we would stop the machine and make adjustments to the weights being put in the back. Do you understand that so far? Yeah? Please speak up if you don't, and I'll try and explain it a bit differently. All right. Associated with these hypotheses are reject HO, the null hypothesis, if the Z value of the sample mean is outside the range for a confidence level of 0.05. This would mean stop the machine and adjusting. Accept HO, the null hypothesis otherwise, i.e. keep the machine running. So we've got a formula here to use to find the value of Z for the problem, and that is that Z is equal to x bar, the population mean, take away the sample mean, take away the population mean, divided by that sigma is the standard deviation for the sample, which has been given, divided by the square root of n. So we put those numbers in, and we get the answer that Z is equal to minus 1.8. Remember, the Z value is how many is it from the mean. So we're talking about 1.8 standard deviations. We're looking at a two-tailed test to 0.05 level of significance. Okay, so we're looking for Z values between minus 1.96 and plus 1.96. From the table, it can be seen that the Z values for a two-tailed test are plus minus 1.96. Since the Z values for this sample is within this range, the null hypothesis is accepted and the machine should not be adjusted. So thinking about our normal distribution here, yep, we've got two Z values, one above and one below, at minus 1.96 and plus 1.96. They're the areas where we would accept the alternative hypotheses and adjust. But our data is saying we're coming in plus and minus 1.8. And therefore, we accept the null hypothesis in the middle, the 95% bit. Yep. Okay, so although there's signs that the weight of the bags is going out, according to the level of acceptance in over and underweight bags, there's not the statistical proof that they're outside the 5% level of confidence. Right? So, we've got a couple of problems. There's a couple of problems for you to have a go at yourselves. First of all, a batch of cables produced by a manufacturer having a mean breaking strength of 2,000 kilonewtons and a standard deviation of 100 kilonewtons. Sample of 50 cables is found a breaking strength of 2,050 kilonewtons. Test the hypothesis that the breaking strength of the sample is the breaking strength of the population from which it is drawn at a level of significance of 0.01. So you've got a more strict level of significance in that problem. Alright, so what data are we looking for from the question? What is the value of the population mean at 2,000 kilonewtons? What is sigma, standard deviation? And what is the sample mean, x bar? Right. So have a go at that. Make sure you lay everything out in an understandable way, because that's how you're going to be expected to do that problem if you get it in the assignment. And then you've also got the problem on the following page. So, this first problem, it says a batch of cables produced by a manufacturer having a mean breaking strength 2,000 kilonewtons. So that's your population mean, mu. That's what you would expect the mean to be if all is well. Yeah? A sample of 50 cables is found to have a mean breaking strength of 2,050 kilonewtons. Yeah, so that's your sample mean, x bar. And then you've been given a standard deviation of, where is it? Somewhere, that's there somewhere. 100 kilonewtons, okay, and your sample size, n, is 50. So let's put that on there as well. And is equal to 50. First thing you should do is, from the word in the question, pick out your null hypothesis, HO. That has to be, in this case, that these two things, it says, are equal. Yeah? So the null hypothesis is that mu is equal to x bar. So you're saying there's no difference between the population mean and the mean of the sample. Remember, there's always going to be a level of significance to think about. Alright, we're not testing if they're exactly equal, but whether they're equal to a confidence level or a level of significance. Then we need to think about what our alternative hypothesis. So let's put this in here. Null and the alternative H1. In this case, what does it say? It says test the hypothesis that the breaking strength of the sample, so that's x bar, is greater than the breaking strength of the population. So There's your null hypothesis. So if we're only looking at greater than, is it a one-tiled or is it a two-tiled test? So therefore, this requires one-tiled test on the greater than side. So if we sketch the normal distribution as we're looking at it here, there's our mean of 2,000 kilonewtons. Okay, we're interested only in the 5% on that side. So we've got a one-tailed test greater than, because it's value across here, positive net values. We're only interested in that one positive side in this case. Yeah. So then we can find our Z value, and that is equal to, and I think you've all done this, the confusion is in finding, so we need this equal to X bar, which is 2050, minus mu, which is 2000, all over the standard deviation, which is 100, over the square root of the sample size, which was 50, and I believe you get an answer of plus or minus 3.54. Am I correct? Yeah. And from the table, what is the Z value for level of significance 0.05? 0.01, sorry. Z value for one-tail test at significance level is, and I'm trying to show you here a way that you'd lay this problem out in an assignment question. So what was that Z value for level significance of 0.01? So that's, and in this case we're only interested in the positive side. You looked at the one-tail test there, yeah? Alright. So what we can say is population, sorry, sample Z value is greater than 2.33. Therefore, null hypothesis is rejected, except alternative hypothesis. Sample is greater than population. So that level of confidence. Yeah. All right. The second problem, internal diameter of pipe has a mean diameter of 3, so mu is equal to 3 centimeters. Standard deviation, sigma, 0.015 centimeters. Sample size n is 30, which is okay. There's 30 or more in this method. Measurements are taken, and the mean of sample is 3.0078. Test the hypothesis that the mean diameter of the pipe was 3 centimeters at the level of significance of 0.01. So what we're doing is, what's the null hypothesis here? Mu equals the x bar. Yeah. Now if we're going to test that it is absolutely equal to that level of confidence, then we have to reject everything else. So our alternative hypothesis is that mu is not equal to x bar. Therefore, it is a two-tailed test. So we're looking at a situation like so, and we're going 0.01. Yeah, that's what we're looking at. So it's 1%, so it's 0.5% that side, and 0.5% that side are region. Right? At this time, the null hypothesis for 0.01 is 99%. Okay? And then that's just like before, so we find our Z value, which is 3.0078 minus 3 all over 0.015 divided by root 30. Should have got 2.85 plus or minus, yeah. Okay. And the Z value, table Z value for 0.01 two-tailed test is plus or minus 2.5, 2.58. Yeah. So what do we do then? Therefore, reject null and accept. And accept alternative. Sample. And in this case, sample mean is outside population mean. Alright, words to that effect. So the null hypothesis is rejected yet again. So now, having seen the working and had a chat about the working of those two, have a go with that last extra one again. Right, gents, let's take a quick look at this last question. So, in this machine produces ball bearings having a mean diameter, alpha, of 0.50 centimeters. Sample of 10, n equals 10. Ball bearings is drawn at random, and the sample mean, x bar, is equal to 0.53 centimeters. Standard deviation is equal to 0.03 centimeters. Test the hypothesis that the mean diameter is 0.5. So the null hypothesis H0 is alpha is sorry, that's not alpha, is that? It's mu. Mu. Mu is equal to x bar. The alternative hypothesis is, so it says, test the hypothesis that the mean diameter is, so therefore the alternative must be anything but that, minus a not equal to, and therefore we want to do a total test. Calculating the Z value, that is 0.53 minus 0.5 over standard deviation 0.03 root 10. What did you get for that? Plus or minus 3.16. Table value for, so this is a table value for 0.05 LOS is, so what's the table value for 0.05 level of significance on a two-tailed text? Minus 1.96. Therefore, B, table value for 0.01 LOS is, so the sorry, .05. That level of significance, just shorten it. Sorry. Just trying to mean no right less. Oh. No. How about if I put it in capitals? I think that would be clearer, wouldn't it? LOS, level of significance. Alright? So with a table value for 0.01, LOS is table value for 0.01 level of significance is plus or minus 2.58. Therefore, Yes. So there's entry. If you look in your book, if you bought it, you'll find there's entries for, I think, 2 others on the right. The 2 final ones. So I think that's 0.005, which is 0.5% for the critical regions, and 0.002, which is 0.2%. Right? But I'm not going to be giving you problems to that level of significance anyway.